Okay, we're going to pick up right where we left off in section 5.1. We are going to verify that the equation is an identity. And so you've got some natural logs here. The reason that you see all these absolute value signs is because natural log or any kind of log has to have a positive argument. That's the only reason those are there. And then to figure this out, you want to get the left side to look like the natural log of tangent x. So tangent, remember, sine over cosine, and secant is 1 over cosine. So I think the first thing that I would do here is I would just change secant to 1 over cosine instead of secant. So natural log of the absolute value of sine x plus the natural log of the absolute value of 1 over cosine x. So I just replaced secant x with 1 over cosine. All right, and now I'm going to use my rules for logs. If I add two logs with like bases, that means I can multiply the arguments. So I can write this as natural log of the product, absolute value of sine x times the absolute value of 1 over cosine x. And so that's just applying the rule for logarithms, a rule for logarithms. And now I can just write that as sine over cosine, because that's what it is. And that is tangent. So natural log of tangent x. So that one, I mean, there wasn't really much to that. It's just they wanted you to apply the rule for logs to do that. So it's not anything major there. All right, so sometimes the only way to verify an identity is to manipulate both sides of the equation kind of at the same time, but kind of independently of each other, trying to make them look the same. So you don't just start with the left side and work toward the right side. You kind of work with both sides at the same time, trying to make them look like something that is the same. So the first thing I would notice with this one is just that you've got a cotangent squared x on the right, and you don't have anything squared on the left. So that makes me think, yeah, I need to go ahead and multiply that denominator by 1 minus sine x, multiply that denominator on the left by its conjugate so that I can have a square something. And it'll end up being a square cosine. So that would be the first thing I would do. I would go ahead and just multiply that fraction by the conjugate of the denominator. And that would give me sine x minus sine squared x over 1 minus sine squared x. And we know that 1 minus sine squared x, hopefully, is cosine squared x, because that is just one of those Pythagorean identities I was showing you in class, where you've got sine squared x plus cosine squared x is 1, which means that 1 minus sine squared x is cosine squared x. So on the left side at this point, I've got sines and cosines. On the right side, I've got cosecant and cotangent. So a good thing sometimes to do is to just change everything to sines and cosines. So I'm going to work with the right side now and see if I can get it to look like the left side. So I'm going to change cosecant to 1 over sine, and I'm going to change cotangent to cosine squared x over sine squared x. We've got there a complex fraction. And if you have a complex fraction, a good thing to do to get rid of all those little denominators is to just multiply the top and the bottom of that whole fraction by sine squared x. And so you're going to be multiplying this whole thing by that whole thing. So you're going to have to distribute this like this. So if you do that, you're going to get sine x minus sine squared x over, now your sine squareds are going to cancel out right there, and you're going to just have cosine squared x on the bottom. And actually now the two sides are the same. You got the left side to be sine x minus sine squared x over cosine squared x, and the right side to be sine x minus sine squared x over cosine squared x. So this is just another strategy. You didn't have to do this problem this way, but sometimes it's easier if you see where you're going to just work with both sides of the equation and get them to look the same. Normally, usually, most of the time, you're going to start with the left side and manipulate it until it looks like the right side. But sometimes it may be that you can get the two sides to look alike by changing both sides. All right, write x squared plus 9 as a function of theta, where 0 is less than theta is less than pi over 2, by making the substitution x equals 3 tangent theta. And you may be wondering, why would I want to do that? And the answer is calculus. So we're going to substitute 3 tangent theta for x. We'll have the square root of 3 tangent theta squared plus 9. And that would be the square root of 9 tangent squared theta plus 9. And if we factor that 9 out, we will have 9 times tangent squared theta plus 1. And then that would And then we should look at that tangent squared theta plus 1 and think Pythagorean identity. All right. You may have I hope you have the Pythagorean identity for sine and cosine memorized already, which is just that sine squared theta or sine squared x plus cosine squared x equals 1. Now you can get the other two identities, as I was mentioning today, just by dividing through by sine squared or cosine squared. You're going to divide through this equation by cosine squared x so that you can get something that has tangent squared x in it. Because if you divide this equation, sine squared x plus cosine squared x equals 1, by cosine squared x, the first term you're going to have is going to be tangent squared. So I'm going to divide that equation through by cosine squared x, and that gives me that other Pythagorean identity, which says that tangent squared x plus 1 is equal to secant squared x. So I've got tangent squared theta plus 1. It is equal to secant squared theta. So square root of 9 secant squared theta. And if I take the square root, that's just 3 secant theta. So I have written the algebraic expression square root of x squared plus 9 as a trigonometric function. Okay, we're going to move right on ahead through section 5.2. We have to finish chapter 5, chapter 6, and chapter 10 before the year is over, and we don't have much time left. We need to move forward at a better pace and not get bogged down. We need to make sure that we're making use of all of the resources I've given you, including notes, videos, all those things. I just want to make sure that everybody's time is being maximized because there are some people that come in that are ready to go forward. Think about trying to get some of those questions answered either by emailing me or sometime before class. That way we can move forward. We got to go. We got to keep moving. We got to go, 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 go. All right, so it might be tempting to think that sine 60 would be the same thing as sine 30 plus sine 30. Sadly, no, it is not. Sine 60, as you should know, is the square root of 3 over 2, and sine 30 plus sine 30 is 1/2 plus 1/2, which is 1, and the square root of 3 over 2 is not the same thing as 1. So no, sine 60 is not sine 30 plus sine 30. Is there a way to write something like sine u plus v or sine u minus v in terms of u and v? And there is, and there's a way to derive it, but we're not going to do that. I'm just going to show you the sum and difference formulas for sine and cosine and tangent. So here we go. The sum and difference formulas look like this. We're going to go through each one because we will have to memorize these. And so I'm going to kind of help you see that there is some amount of organization here. So for the sine formulas, they look like this: sine u plus v, sine u minus v. First of all, you will notice that the sum formula for sine is a sum. You will notice that the difference formula for sine is a difference. That's one thing you can memorize easily. The other thing is that both of these formulas have sine, cosine, cosine, sine. Sine, cosine, cosine, sine. The right side of these two equations look exactly alike. It's sine u, cosine v, cosine u, sine v. They're the same. They're exactly the same. The only difference is that for the sum, it's a sum. For the difference, it's a difference. The sum and difference formulas for cosine look like these. This time, the sum formula is a difference, and the difference formula is a sum. So for cosine, the signs don't match. The other thing is that for the cosine formulas, you've got cosine, cosine, sine, sine. Cosine, cosine, sine, sine. You've got cosine u, cosine v, sine u, sine v. Cosine u, cosine v, sine u, sine v. Both of the right sides look exactly the same except for the sign in the middle. So you do need to know these particular formulas. If you are going to memorize something, find relationships within it that give you fewer things that you actually have to memorize. You don't have to memorize so much. You have reduced it down to this groove, this sine, cosine, cosine, sine, and now all you have to do is remember plus, plus, minus, minus. There it is. We reduced it down to fewer things to memorize. Then with the cosine formulas, you just remember the signs are opposite. So the plus is a minus, the minus is a plus. And for the cosine formulas, it's cosine, cosine, sine, sine, cosine, cosine, sine, sine. So reduce it down to smaller things that relate to each other. That's how you memorize. All right, the tangent formulas are a little more complicated, although they do look the same. The u plus v has a plus on top. The u minus v has a minus on top. Cosine 15 degrees. If you're going to find cosine 15 degrees, you're not going to punch it into your calculator because you want to find the exact values. The calculator will give you a decimal. That is not the exact value. That is an approximation of the value. We want the exact value. And now that we know the sum and difference formulas for sine and cosine, we can do that because we know that 15 is the same thing as 45 minus 30. And because I know the cosine of 45, and I know the cosine of 30, and I know the sine of 45 and the sine of 30, I can use this formula right here to help me find the exact value of cosine 15. Cosine 15 is cosine of the quantity 45 minus 30, and the cosine of the quantity 45 minus 30 is cosine 45 cosine 30 plus sine 45 sine 30. And since I know those values, I know that cosine 45 is square root of 2 over 2 over 1 over the square root of 2. Square root of 3 over 2 for cosine 30, and then sine 45 is 1 over the square root of 2, and sine 30 is 1/2. And that's it. I can rationalize that by multiplying by square root of 2 over square root of 2, and then I will be done. This is the exact value of cosine 15, square root of 6 plus square root of 2 over 4. Okay, so here you have sine of 11 pi over 12. And so this actually could be broken up into a couple different ways. You could break it up into sine 2 pi over 12 and then 9 pi over 12. You could break it up into 3 pi over 12 and 8 pi over 12. So there won't always just be one way that you could break it up. We are going to just break it up the second way. That is going to be the sine of 3 pi over 12 plus 8 pi over 12. That adds up to 11 pi over 12, so that's good. And just let's reduce those fractions. So sine pi over 4 plus 2 pi over 3, 2/3 pi. And so now we just use the formula sine, cosine, cosine, sine, and it's going to be positive. It's going to be plus. So sine pi over 4 cosine 2 pi over 3 plus cosine pi over 4 sine 2 pi over 3. And now we just look at our unit circle or get it out of our brain, which we can for at least for the pi over 4. And we will have 1 over the square root of 2 times negative 1/2 plus 1 over the square root of 2 times square root of 3 over 2. And now we just multiply it out. And this is what we will get. And we can rationalize that by multiplying by the square root of 2 over the square root of 2. And you will get negative square root of 2 plus the square root of 6 over 4. And that is the exact value for sine 11 pi over 12. And this looks better when you put the positive square root first. It's just a better looking notation. And so there you go. All right, find the exact value of this expression. So for this one, you're going backwards. It's got sine, cosine, cosine, sine. It's got plus. It's the sum formula for sine. So that means that this is just sine of the quantity 25 plus 35. It's just the right side of the formula, and the left side would be sine 25 plus 35. So this equals sine 25 plus 35, that quantity, which is just sine 60, which we know is square root of 3 over 2. Okay, so there are a lot of things to memorize in this chapter. All right, example 3, find the exact value of cosine alpha minus beta, given that sine alpha is negative 4/5 and cosine beta is negative 5/8 for alpha in the third quadrant and beta in quadrant 2. Okay, that's a lot of information. That's a lot of stipulations that we have to deal with. So the first thing we're going to do is figure out where alpha and beta are in the xy plane and take a look at the triangles that represent the sides that go with that angle. So we know that alpha is in the third quadrant, so it's right down there. And we know that it has a sine of negative 4/5. So the opposite over hypotenuse for this angle is 4/5. We can use the Pythagorean theorem to find the other side. So the other side is 3. So you've got the whole triangle. You can find the sine for alpha, the cosine for alpha. They'll both be negative in the third quadrant. Then you've got cosine beta is negative 5/8. So what is beta? It's in the second quadrant. It's an angle in the second quadrant. And it says its cosine is negative 5/8. So that means adjacent over hypotenuse is 5/8. So there are those sides. Use the Pythagorean theorem to find the other side. So y squared is 39, which means that that other side is the square root of 39. So now we've got the whole triangle. We can find the sine, the cosine, whatever we need to of beta. So what is the question? Question is find the value of cosine alpha minus beta. So cosine alpha minus beta, according to the difference formula for cosine, that is going to be cosine alpha, cosine beta, plus sine alpha, sine beta. And now all we have to do is just fill in those values. So cosine alpha is coming from that triangle in the third quadrant. Cosine is adjacent over hypotenuse, so that's negative 3/5. Cosine beta is the second quadrant. Cosine is adjacent over hypotenuse, so negative 5/8. And then you've got sine alpha. Alpha is in the third quadrant, so it is negative, and it's opposite over hypotenuse, negative 4/5. And then sine beta in the second quadrant is going to be positive. Sine is positive in the second quadrant. And so that's square root of 39/8. And there you just multiply it out, add it up, and you are done. So that's 15 minus 4 square root of 39/40. And that cannot be reduced. Okay, find the exact value of this. All right. This is sine of some angle plus some other angle. First of all, we got to figure out what are these angles? Where are they? What do they mean? Okay, so we're looking at the angle whose tangent is negative 9/40. Remember that inverse tangent has a range of negative pi/2 to pi/2. That means the fourth and the first quadrants. So we're looking for an angle whose tangent is negative 9/40. That's a negative value, so that is going to happen in the fourth quadrant. So this angle, whatever it happens to be, has a tangent of negative 9/40. So opposite over adjacent is 9/40. If you use the Pythagorean theorem, you can find out that the hypotenuse is 41. Inverse cosine of 8/17. So the angle whose cosine is 8/17. Remember the range for inverse cosine is 0 to pi, the first two quadrants. And so that angle has a positive cosine. That is going to be in the first quadrant. And so we know it has cosine 8/17. So that's adjacent over hypotenuse is 8/17. And if you use the Pythagorean theorem, you can find out that the other side is 15. So we have these two angles. I'm going to call that one A and that one B. So what we really have here is sine of A plus B. That equals sine A cosine B plus cosine A sine B. So now we just need to fill in the values. The sine of angle A, that's in the fourth quadrant, is going to be negative, and it is opposite over hypotenuse, so negative 9/41. And then cosine of B, that's the angle up in the first quadrant, and that is going to be adjacent over hypotenuse. That's 8/17. And then we've got cosine A, that's in the fourth quadrant again. Cosine is positive in the fourth quadrant, and so that is adjacent over hypotenuse, 40/41. And then sine B, that's in the first quadrant. It is positive, opposite over hypotenuse. And when we add that up, we just multiply it out, negative 72/697 plus 40 times 15 is 600/697. And when you add that up, you just get 528/697. And that is not reducible. So there you have it. That's it. We can use the fact that tangent theta is sine over cosine to derive the sum and difference formulas for tangent. So tangent of u plus v is equal to sine u plus v over cosine u plus v, because that's what tangent is, sine over cosine. I already know the formulas for sine u plus v, or I'm learning those formulas for sine and cosine u plus v, and so just write those down. That's going to be sine u cosine v plus cosine u sine v over cosine u cosine v minus sine u sine v. All right, now the way to write the tangent formula in the form of it, you can write it in a lot of different ways, but everybody wants it to have a 1 right there in the denominator. The first thing in the denominator should be a 1. I don't know why. It's just the way it's preferred. So if you're deriving it, just remind yourself, okay, I want a 1 right there, first thing in the denominator. So if I just divide the whole fraction by cosine u cosine v, I'll have that 1. So that's what I'm going to do. Divide every term in that fraction by cosine u cosine v. All right, and if I go ahead and start canceling things, I can see that the first thing in my numerator is tangent u. And the second thing in my numerator, if I cancel those cosine u's, is sine v over cosine v, so that's tangent v. And then in my denominator, that first fraction is just 1, and the second fraction is just tangent u, tangent v, because it's sine u over cosine u, sine v over cosine v. So that's the formula. That's the sum formula for tangent, and you could do the difference formula the same way using sine and cosine. Okay, so you want to take the tangent of 255. You need to figure out how to break 255 up into two angles that you could recognize and know the values of. So if you remember, 225 is an angle that you know, and 30 is an angle that you know. All right, so we've got tangent 225 plus 30. Use the formula that we just derived. You will have tangent 225 plus tangent 30 over 1 minus tangent 225 tangent 30. And now you just figure out what those values are. You're dealing with 225, which is over here. It's related to 45. In the third quadrant, tangent is positive because sine and cosine are both negative. So we're going to have a positive 1 for that. And then tangent 30 is 1 over the square root of 3. And then the denominator, you're just going to have 1 minus 1 times, it's 1 over the square root of 3. Square root of 3 over square root of 3. And remember, I'm going to have to distribute that there, and I have to distribute that here. And so I'm going to end up with the square root of 3 plus 1 over the square root of 3 minus 1. And then I'm going to have to multiply that by the conjugate of the denominator to rationalize it. And if I do that, I'm just going to end up with 3 plus 2 square root of 3 plus 1 on the top and 3 minus 1 on the bottom, and you get 2 plus the square root of 3. So that is the exact value for the tangent of 255. Okay, the cofunction identities. Remember that the cofunction identities simply state that the sine, cosine, or tangent of an angle is equal to the cosecant, secant, or cotangent of its complement. So when I say sine theta is equal to cosine pi over 2 minus theta, I'm saying that the sine of theta is equal to the cosine of theta's complement, because that's what cosine means, sine of the complement. So same thing with cotangent and secant and cosecant. If you take the tangent of an angle, that's the same thing as the cotangent of that angle's complement. Secant of an angle is equal to the cosecant of that angle's complement. And so those are the cofunction identities. We already talked about those in the previous chapter. And then the periodic identities just means that if you take, say, pi over 6, and you take the sine of pi over 6, if you look at your unit circle, that is the square root of 3 over 2. If you spin around the circle one time, 2 pi, and you come back there, that's going to have the same sign. Sine pi over 6 plus 2 pi is still the same thing as it was. So you can add 2 pi. Remember that tangent and cotangent only have a period of pi. And so in that case, if you were at pi over 6 and you took the tangent, all you'd have to do is add pi and come down here, and you would have the same tangent again. So tangent and cotangent repeat more quickly. You repeat every pi radians. So halfway around the circle, you get the same value again. Okay, so verify the cofunction identity, sine pi over 2 minus theta is equal to cosine theta. So we know this is a true identity because it was in the table we just looked at for cofunctions, but we're going to use our difference formula for sine to prove that it's true. So sine pi over 2 minus theta is just equal to sine pi over 2 cosine theta minus cosine pi over 2 sine theta. And so all we have to do is fill in those values. We know sine pi over 2 is 1, and we know that cosine pi over 2 is 0. So we just end up with cosine theta, and therefore we have proved that sine pi over 2 minus theta is equal to cosine theta. Okay, now I want to verify this identity. Cosine of the quantity x plus y times cosine of the quantity x minus y is equal to cosine squared x minus sine squared y. So the first thing I'm going to do is use that formula for the cosine of a sum and the cosine of a difference to write this all out in that way. So I've got cosine x plus y times cosine x minus y, which is just going to be cosine x cosine y minus sine x sine y. All of that times cosine x cosine y plus sine x sine y. So I just used the sum and difference formulas for cosine to write that out. And now I can notice that these are conjugates. It's just a plus and a minus for those middle signs. Otherwise, they're exactly the same. So these are conjugates. And remember that when you multiply conjugates, you get a difference of squares. A plus b times a minus b is a squared minus b squared. So when I multiply these out, I'm going to get the first thing squared, which is cosine squared x cosine squared y minus sine squared x sine squared y. So that's what I've got. Now, if I look over here at what I'm trying to get to, the first thing I see is that I have cosine squared x. So wherever I see an x, I'm dealing with cosine. So I'm going to try to make it so that anything with an x is expressed in terms of cosine or cosine squared. And so the first thing over here is already cosine squared x. But over here, I've got this sine squared x. I don't want sine to be associated with x. I want cosine to be associated with x. So I want to rewrite that, and I'm going to use the Pythagorean identity to do that because I know that sine squared x plus cosine squared x is equal to 1. And that means that sine squared x is equal to 1 minus cosine squared x. I'm going to take that and substitute that in for sine squared x right there. So that is what I'm going to do, first of all. So cosine squared x, cosine squared y, that would stay the same. And then I'm just substituting for sine squared x. I'm putting 1 minus cosine squared x. Okay, and now I'm looking at the sine squared y on the right side of the equation that we started with. I'm trying to get my y's to be associated with sine squared. So in that first expression right here, you can see that you've got a cosine squared associated with y, and that I don't want that. I want that to be associated with sine squared. So just like I wrote sine squared as 1 minus cosine squared, I can write cosine squared as 1 minus sine squared. So that's what I'm going to do right there. I'm going to rewrite cosine squared y as 1 minus sine squared y. And then on the right side right here, that is already in terms of sine squared, so I'm just going to put that. I'm going to leave it the way it is. All right, so next, I'm going to distribute that cosine squared x through the parentheses. And then I'm going to distribute this sine squared y through this parentheses. And now, if I distribute that minus sign, that cosine squared x sine squared y is going to cancel out, and I'm going to just end up with what I wanted, which was cosine squared x minus sine squared y. Sum of a sine x and b cosine x as a single term. For real numbers a, b, and x, a sine x plus b cosine x is equal to k sine x plus alpha, where k is equal to the square root of a squared plus b squared, and alpha satisfies cosine alpha equals a over k, and sine alpha equals b over k. So changing the form of an algebraic expression is very important in calculus. And so that's why we're doing this. It seems random, but it's actually not, but we're not going to derive it right now. So we're just going to go ahead and change using these rules that you see right here. We're going to change 5 sine x minus 12 cosine x into the form k sine x plus alpha. So first thing we see is that k is going to be the square root of a squared plus b squared, where a and b are the coefficients on sine and cosine. Our a is 5, our b is negative 12, and so we're going to go ahead and take the square root of 5 squared plus 12 squared. And that's going to be the square root of 169, which is 13. So we've got our k. We want alpha to be an angle such that the cosine of alpha is equal to a over k. A, remember, is 5. K is 13. So we're trying to find an angle whose cosine is 5/13. And then the next thing we have is that sine alpha is supposed to equal b over k. So we need to find an angle that has a sine of negative 12 over 13. So we're looking for an angle that has a positive cosine, so greater than 0, because cosine alpha is 5/13, positive 5/13. We want that same angle to have a sine that's negative, and we want sine alpha to be negative 12/13. So which quadrant are we in? If we're in a quadrant where cosine is positive and sine is negative, that would be the 4th quadrant. Okay, so we're looking for an angle in the 4th quadrant that has a cosine of 5/13 and a sine of negative 12/13. So we're going to say inverse cosine of 5/13. If we punch that into the calculator, we get about 67.4 degrees. Now that's in the 1st quadrant because the range for inverse cosine is 1st and 2nd quadrants, so that's what your calculator is going to tell you. But that's not really the angle I want. I want the one in the 4th quadrant that has that cosine. So I would need to subtract 67.4 from 360 to get the actual angle that we're looking for alpha. So alpha is going to be 292.6 about. And so our expression that we would write for a sine x plus b cosine x is going to be k square root of 13 sine of the quantity x plus alpha. And in this case, alpha is 292.6.